Okay, I'm going to pass a book around. I do not have a book for this course other than my own, but if you were to buy a book for this course, this would probably be a good one. This was what was recommended by the previous instructor, and I've looked through this book a number of times, and it's a decent book. And if you like a big fat book that doesn't cost a lot of money, this is a good one. And the difference between what he does and what I do, in one respect, is he says, okay, now I'm going to look at all the major brands of PLCs, not just one or two, and I'm going to look at how each of them does a certain thing. And he does that, slice and dice it all the way across. And it's. I looked at this book and I thought, boy, anybody who would be willing to do that uh, either is really, really dedicated or he's really dumb. I think he's really dedicated. This guy's a pretty good source. We actually need all six major brands to survive in the real world is another question. But I think he wants to basically cover all the bases, and you can pick which one you want to use, and then you can look at that. Most of his examples are from the older Siemens, not from the newer Siemens. The Siemens brand really restructured about 10, 15 years ago, and they went from what the Germans had done to now what they thought the American market and the world market would like. So that's what's the difference between what you see in here a little bit and what I have from the Siemens side, because I didn't join the Siemens band until about 10 years ago to get started on it. But anyway, I'll pass it around. If anybody wants a copy of it, they can buy it. It doesn't hurt to have a copy of the book if you like to, if you are so interested. But that's Erickson, his book. So people have asked me, and I probably failed to really adequately explain what I'm looking for a book report, or not a report, but a lab report. And also, I owe you, and I will do this, I just haven't done it yet, a more complete list on the syllabus of the labs that are available that you can do, the higher point labs at the end. But page 1 would be a title page, your names, and the lab number. And the lab number has to be the lab number that's on the syllabus, okay? Like lab 2.1, it has to say 2.1. I will not look at it and say, well, I'm going to have to figure out whether this is one of my labs or it's Joe's lab over from the other campus or whatever. And then the name of the lab and your date, all of that kind of stuff, okay? Now, you can put that at the top or you can put it on the first page totally, but then I want proof of what you did. In other words, screenshots, as much as possible. I cannot possibly grade you all by signing off on your labs, but I can look at your lab and tell you very quickly whether or not you did it. And I can tell with not infinite detail, but I'm pretty good at being able to decipher if you are doing the lab that you say you're doing. Okay, we have so many labs to do, and 14 weeks is not enough time to do this course justice. But the whole gist of this course is to get you as much as possible into the lab and get you accustomed to doing these labs and getting you accustomed to the software and then starting to write some meaningful programs. That's the whole reason for this course. And not to turn you into a controls programmer, but it's to kind of maybe get you started on that path if that's what you want to do. And then a conclusion, an explanation of what you did. The conclusion, what this lab taught you. It could be 3 sentences, it could be 5 sentences, it could be 8 sentences, more than 1 sentence, but something that is what meaningful in this lab. Pause for 5 to 10 minutes, think about what you did in that lab. It's a pause before you race to the next thing you do, okay? Conclusions don't have to be long, they don't have to be, half a page or a page in length. You don't have to prove to me that you did the lab. Just what did you learn? Think about this lab for 5 minutes, 10 minutes before you go to the next activity, whatever it is. Stop and think. What did I learn? Anybody have any questions about that? This is important. This the number of the lab. It's very important because that's how I grade it. I have, oh, and also, did you do it with Allen Bradley or Siemens? Or did you claim it for both? So if you did it for both, you have to have an explanation for both, and then you say, I did it for Allen Bradley, and you have a section for Siemens, and then you get 4 points. You get 2 for Allen Bradley and 2 for Siemens, okay? You cannot get 2 for Allen Bradley, 2 for Siemens, and then 2 for Allen Bradley with the HMI, and 2 for Siemens with the HMI. You can't double dip, you can't double. You can double dip, but you can't double the double dip. All right, and does anybody not understand that? And you can only get 20 points up to lab 8.3 or something like that. So only half of your points can be before that division of in chapter 8. After that, you have to get points from other sources. You have to go to other places. You have to go beyond chapter 8 to get points. I think it's 8.2 or something like that. I forget exactly which one it is, but it's after the simple labs. I called through some point there the simple labs. I don't know exactly how to do it. But anyway, that gets you a little bit better explanation, and hopefully that gets you a little bit of an idea. Okay, so we did talk about timers and counters some, not a lot, but a little bit, and I want to continue on doing that. Okay, so you have differences between Allen Bradley and Siemens with timers and counters. They're subtle. They both have counters, they both have timers, but the differences are somewhat subtle, okay? Now, both of them have timers that are non-retentive and retentive. What do I mean by non-retentive? That means when you turn the input off, it goes back to 0. It resets back to a 0 count. And it counts 1 count for every 1 millisecond. So 1 millisecond equals 1 count. If you're on for 10 milliseconds, the count in the accumulated value says 10. And it's by millisecond. And both of them have the same counter type timer activity. And they both count up to a 32-bit, 2 to the 32nd, or 2 to the 31st minus 1. A big number. It's a very long time, okay? Or very long count, either way. Now, what do I mean by non-retentive? Non-retentive means when you turn it off, it goes back to 0. When it is retentive, that means when you turn it off, it stays where it is, and then it moves from that point on. 99 times out of 100, this is the one you're going to use, okay? Very rarely is this one ever used, all right? Very rare. Now, I'll give you an example of this type of timer, this retentive type of timer, all right? It's called Professor Evans's oatmeal, okay? So when I get up in the morning, I yawn a couple times and whatever else, and then I go in and get my oatmeal. So I get oatmeal, and I put it in the I put some water in it, and I put it in the microwave, right? I put the oatmeal in the bowl, put it in the microwave. Well, the instructions say 1.5 minutes, but I've observed over the years that if I go for 1.5 minutes and don't watch it, what happens? Sometimes it boils over and it makes a mess in the microwave, which I do not want to do. So I have not automated this process, but I could automate it to actually have a little photo eye at the top of the bowl that says when I see bubbles coming up above the level of that, I'll turn it off until the bubbles go back down. But then once the bubbles go back down, it lets the microwave start again. So that's a retentive timer. Until it goes to 1.5 minutes, then it shuts off, my oatmeal is ready to go, and I'm a happy camper because I didn't have to clean up my microwave. That's a retentive timer, okay? So if you think retentive timer, think Professor Evans's oatmeal in the morning, you got it. It goes up, it goes up, it goes up, it goes up, done. All right, and that actually happens. It happened this morning. I had to shut it off, turn it on, shut it off, turn it on, about 3 times. Now, sometimes it doesn't do it at all. So I just let it rip and it goes for 1.5 minutes. It's done. Tastes the same. It's the same oatmeal. Sometimes either the amount of water or the actual, you understand what I'm saying? It doesn't boil over at all. All right, sometimes it does. So it's a game, but it is real. It's real world and it actually happens. There are other applications, but they're very, very rare. However, non-retentive timers are used all the time. They're everywhere. They're used in a lot of applications, okay? Now, when you have a retentive timer, you have to have a way of turning it off. And I'll show you the differences between the two timers, and one of them is with this retentive timer. You have to have a separate way, a signal that actually resets it, because it doesn't reset by itself. How does a retentive timer reset? When you turn the input off. When you turn the input to it off, it turns off and it goes back to 0. So they both look pretty much like this. They're a block, and I call these my first of my big box types of instructions. It's just a box. They both say TON. Allen Bradley and Siemens both say TON, okay? And they both have an input. They both have an input. When you input to them, they start timing. Simple. A TON starts timing. When they're done, they have a bit over here. Now this is Allen Bradley. This is Siemens. They have a bit over here that's called done. They have a through bit right up here that as soon as this turns on, it enables right here, which you can't use this for anything, but you can use the contact off of the done bit to do something, and I'll show you how that works in a minute. Siemens, on the other hand, the delay, this is a delayed bit. This is your actual output that says it's done. So here, this is the, let's call this TON, let's just call it timer 1. This would be timer 1.EN, and Siemens does it timer 1.IN. Same thing, enable, or the input, or the enable bit. It's the same thing. Allen Bradley carries this through T1.EN and carries it through, but they have a separate done bit that you can access. Siemens, on the other hand, says T1.Q, which is the output, which is the delay. Now, Allen Bradley has a bit called the timer timing bit, T1.timer timing, which is the combination of .IN or .EN, but not .done. So this is equal to this. You don't have to write this, you can write this. Siemens, on the other hand, does not have a timer timing bit. They only have the ability to write T1.IN, but not T1.Q. So you're forced to do this with Siemens. With Allen Bradley, you have this third bit called the TT, or the timer timing bit. So if you want to know when something happens and it's in that timer timing arena, when it's in that, you just use the timer timing bit with Allen Bradley, but with Siemens, you don't have that. You also have, for both of them, you have an accumulated and a preset. A preset, an accumulated value. Now these are integers, or they're dense, double integers. Both of them are dense. They're 32-bit integers. So they have the same thing over here. They have a preset. Siemens have a preset on the left and an accumulated value on the right. Allen Bradley buries all this stuff within the actual. You can get at it, but you don't have to put anything here. You don't have to physically put anything along here. With Siemens, you have to put the preset on the left. You have to put the accumulated value on the right. You have to. Well, if you want an accumulated value, if you don't care, you don't put anything there. But with a preset, you have to put a preset. You have to put this here. You have to put something in there, or it won't work. With Allen Bradley, if you don't put anything in there, it just automatically times 0. It just times immediately, and it's gone, and it keeps on going. But anyway, so that's a TON timer with each of them. Does everybody understand that you have these little idiosyncrasies, but they're basically the same thing? They do basically the same thing. The retentive timer, on the other hand, for Allen Bradley is a little bit different in that it has a separate coil. Now this is the timing diagram for the TON timer. Okay? If you go to preset, then it turns on. If you go no, don't go to preset, it doesn't turn on. Is everybody? Nope, that's a pulse timer. Sorry about that. Here's your Mr. Retentive timer, all right? Or excuse me, non-retentive timer. This is the one that goes back to 0. If you do not end up getting to preset, it doesn't turn on. Here it does turn on because it got the preset. Here it didn't get the preset before it turned off, resets back to 0. Here it starts all over again and goes back to 0. That's a timing diagram that explains how a TON timer works. Now, this is an example of how and again, I'm skipping some of these timers because they're not all that useful. The pulse timer, Allen Bradley doesn't have a pulse timer. It's not that useful. You can build them if you want to. This is an off delay. And again, you can get an off delay by making an on delay with a normally closed contact. So I very rarely ever, I totally ignore TOFs, okay? This is the example of a retentive timer. All right, it does not reset unless you hit the button that says reset, which is this is the reset button. Okay, so you go up to a point, it sticks there. Here's my oatmeal. It goes a little bit more, it goes whatever, it keeps going. It finally gets to preset and turns on. That's a retentive timer. That's the oatmeal example, right? If you have a, well, they show these coils as well. I always use the boxed version. In chapter 1, I talk about the IEC standard version of the languages, the IEC version. And if you go back and you say, now, are you IEC 61131 compliant? You would say yes, and you would use this type of a scenario for your timer. So Siemens has that. Allen Bradley does not. If you ask them if they're 61131 compliant, they'll say, yes, we're compliant, but they really don't have that same set of contacts. This is the way if you were to take a program from Allen Bradley and move it to Siemens or somebody else, and you say, I want to move the IEC equivalent, it's supposed to play and it's supposed to run. Now, whether it actually does or not is another story. Did that book go all the way around? Did everybody get a copy? Did everybody get a chance to look at that book? Did this book get around or did it not get around? No? Okay, this is the other brother book. Did it make it back the first row? Did it make it back? Did you how far back? Go all the way back? Okay, that's okay. Back, 3 rows back. Get them. So that book is, like I said, it's about an $80 to $100 book. If you like a big book that has all the major PLC languages in it, that one does. Whether it's a good book or not, I think it's probably as good of a paid book that you're going to buy. Mine is free, and I'm not saying mine's better than theirs. Mine does a little bit differently, but on the other hand, you decide how you want to do that. But anyway, the block version of these instructions is not the IEC version. This here is the IEC version. But I only use the block version. Why? Because they're simpler. They're simpler to use. And you got all the works in a drawer, you got everything right there, you see everything right in one spot. But it's not IEC compliant. So you decide, that's your choice. But that's what that is. So Siemens gives you both. Allen Bradley just gives you the box. But Allen Bradley says they are IEC compliant, just like Siemens does. And anyway, most people ignore this. But that's what that is, okay? But with the retentive timer, you must have a reset coil. All right. Now counters are the same look. They've got a box, okay? And you notice you can count up you can count down, and you can go up, down. And lab 7.2 is using this up-down counter. I specifically designed it to use that up-down counter. Now, with this counter, you have to pick which one you want to do. A preset counter goes up to preset if it's an up counter. It goes from the preset down to 0 if it's a down counter. Or if it's an up-down counter, it goes to preset, which is like an up counter, but if it goes to 0, it can go through 0, it can go negative. Okay, it turns on, it turns on at preset, it turns on at 0. It's got all kinds of stuff with it. Now, counters work by a leading edge. So every time you see another leading edge, they count by 1, they increment by 1, or they decrement by 1. So every time you see a new off to on transition, they count. You can have no off to on transitions for 3 days. In the instant that you get an off to on transition, it'll count 1. Now, what are these used for? They're used to count parts. What else are they used for? They're useful for troubleshooting. Troubleshooting is one of the reasons that we have counters, because why? You can't see all the things that go on, like the one-shots that you can't see, but you can set a counter for a one-shot and see if it happened. And you say every time that it happened, it increments the count by 1, and that's exactly how you use counters in many cases, is to see if you actually had one-shots that actually happened. Okay, so now Siemens has 3 counters. Allen Bradley has 2 counters. With Allen Bradley, if you have a counter that's an up counter, CTU, and one is CTD that has the same tag, okay, let's call it tag counter 1. Okay. You can count up and down with this counter. You say, what? I can use the same counter to go up and go down. Now, if I put more than one CTD, this does not work. Or more than one CTU, this does not work. But if I have 2, if I have one that goes up and one that comes down with the same tag, it works, okay? All right, now what is wrong with this? Well, you can put one of these on page 1 and one of these on page 30, and it's hard to troubleshoot. But you can do that. That's not good programming, but that's how you can do that. If you want to keep it hard, you can make that happen, okay? But it's not advised. The best thing you can do is to put these right next to each other and see the counter upper and the counter downer go at the same time, okay? One of the biggest differences is these have 3, this has 2, but they do the same thing. All right. This is the old style. We're moving along pretty quickly today because I want to get through chapters 7 and 8. I want to get through chapters 9 and 10 on Wednesday night. I want to get through chapter 11 on next Monday night and then have our test for the midterm on Wednesday night of next week. That's my goal. So if you want to know why I'm speedy tonight, it's because I would like to get through chapter 11 before we have a test. Not that you have a lot of questions on chapter 11. We will have a review and all that kind of stuff, but I'd like to at least get through some of this stuff. We've had 2 nights of, we had 1 night called off and 1 night on holiday, and I'm just wanting to get, okay. So, how do you use these puppies? All right, here's one example. So I have a seal circuit. All right? I turn something on, right? I've turned something on, and that's a push button, okay? Now, if I were to do this and then tie it in with this, what have I gained? All right. Well, this is called a twofer. All right. Or BOGO. Buy one, get one free? Okay, is that what that is? Something like that? So what does this do? It's a seal circuit, but it also has a time delay. It does both. All right, so it does two things at the same time. It sets a seal circuit, but it also has a time delay off of that circuit. Now, that is useful in a lot of areas, but you can use the enable bit down here, this bit right here that turns on right here, to seal your circuit, and there's a time delay in this circuit as well. So when this happens a second later, this thing turns on, the done bit comes on. All right? So again, I'm not trying to say this is the greatest thing since sliced bread, but it does give you two things. It gives you a seal circuit and a time delay. You may use this in circuits. I don't know if you will or not, but it is very useful. I have used this. How's that? I use that kind of thing a lot. Okay, so that is basically here's some examples. Here's some more examples, right? Okay, so here is the counter for Siemens, the up-down counter for Siemens. Count up, count down, reset, and you have to hit the load bit when you put the preset in. You put the value here, you have to turn this on for this to be accepted. This is one of those Siemens exclusives that basically gives you, it ain't done until we say it's done. This is a two-step process. You put a value here for new preset value, and then you hit that, and then this is the new preset value. It's a two-step process. They don't let you just put in a new preset by loading a new number there. No, they really want you to make sure that you're putting it in and loading a new preset. So you have to not only turn on the bit, but you have to also set that other bit as well. All right, now I think I missed something back here, and I got to go back and look at it for a second, okay? I think I missed something. Sorry for this. I may have missed it down. It may be delayed. It may be down here. Well, I'm just going to talk about it, and I can't remember exactly where it's at, but I'm going to just talk about it. Okay, and it's in here someplace. I can't remember exactly where it is, but I'll tell you. It has to do with timers and clocks. Okay. Now, clocks are very different from timers. All right. Used to at one time you had to build your clock from a timer inside the program controller. Not so anymore. There is a clock circuit. Where the heck is that? It's here. I just want to, well, it's in here. I'm sorry I'm having to troubleshoot this myself, but I want to talk about clocks. Yeah, it's later. I'm sorry I went backwards, went the wrong way. Okay, so we're not talking about clocks, except very shortly. Clocks are very important. Why are clocks important in a process? All right, in most applications, you're going to have multiple programmable controllers. You're going to have maybe 2 to 5 to 8 or 10 programmable controllers running a machine. When something happens, what do you want to do? You want to log what happens and the time that it happened, right? You want to have a coordination between the clocks of all the program controllers. That's available. Most of the program controllers that you have, including the ones from Allen Bradley and Siemens, you can coordinate the time between the various program controllers. And you can record that time as Greenwich Mean Time or whatever. You can record that as a time exactly. Now, why is that important? I have an example, all right? This is a good example because it gets you to thinking about in terms of why is clocked time important, okay? One of the projects that I did that was kind of a dud, that was a project, was I helped work on the Cherry Street Bridge. They automated something on the Cherry Street Bridge where they actually took the program controller and they ran the remote I/O underneath on the riverbed floor, and they brought the I/O up on the other side, the east side. Okay, so the controller is on the downtown Toledo side in that tending room. Then they have to run all the way down on the floor of the river, and then they come up on the other side, and on the other side of the river is the controls for the I/O that raises and lowers the bridge. All right, so this was before you probably are all born. It was probably 96, 97, somewhere along in there. I worked for a company just a little bit that basically did that automation. I was the second in command. In other words, I was the guy that if the first guy fell off or died or whatever, they had to have somebody that moved in and took over and didn't drop the ball and kept the ball going, okay? So out of this project, I got all of 2 billable hours at $25 an hour and a Wendy's Happy Meal. It was maybe better than a Wendy's Happy Meal. It was a Wendy's meal of some kind. I had a Wendy's meal out of it. Okay, I didn't get anything out of it. Basically, I was just there. I did this kind of stuff on the side. If somebody needed something, I would help them, that type of thing. And wasn't always free, but it was not always not very lucrative. But anyway, what happened? Well, soon after this thing was installed, the guy, the mayor at the time was Carty Pinkbeiner. And you probably heard the name Carty Pinkbeiner if you lived in Toledo for a while, but he was mayor and he wasn't mayor, and now he's been back to being mayor, and he's not a mayor again. So anyway, Carty believed in decorating the world, and he put flags along on the bridge. So this day on a Sunday afternoon, the flags were flying, a ship was coming in, and the tender did not see anybody on the bridge because of the flags, and he let the bridge come up. And there was somebody walking on the bridge, an elderly lady, and she took a slide. Now, she went down into the inner workings of the thing. She didn't get hurt. She was okay and all that kind of stuff. But the guy who programmed this thing, I heard about this. I said, Roger, I called him and said, Roger, what happened? He said, don't worry. He said, we tagged everything and everything was printed out. This is exactly what happened with who did it and how it was done. Okay? It was printed out. And it was dated and printed, and all that was done with a clock and the time, and it was all done. Thank you, Roger. I got PE after my name. I'm not inclined to be somebody that wants to walk into something that's stupid. And if it hadn't been provable that it was a tender that pushed the button, what do you think would have been? Who would have been blamed? The programmer. All right. And it was provable. Everything was timed and stamp dated as to exactly who did what, when, and how. Okay, is time important? You betcha. It can be very important. How things happen in what order. And there was never any question, there was never any doubt that the operator pushed the button. But I'm sitting there reading these newspaper dailies and things. Boy, I hope that Roger was very complete and very good, and he did a very good job, and I'm very thankful. And I'm sitting there just thinking, my name is on this thing. Not that I did anything. I didn't do anything, but I was listed as the second. William T. Evans, PE. Not good. But it was done correctly, and it worked. And it printed out the time exactly and what happened and when it happened, and good to go. Okay, so timing is extremely important. Not to be confused with, that's a clock issue, it's not a timing issue. Please make sure that you understand that your PLC has clocks in it and that do keep track of time, and that you should keep track of important events in an orderly manner to make sure that if anything ever happened, you will keep you'll keep an accurate record and print it out if necessary what actually happened, when it happened. Okay. That's my story. It's, you know, I've had a few of those. That was an interesting one. That lady going down that thing, I can just see her, a big slide going straight down into there. Anyway, she's okay. She didn't get hurt, nothing, maybe no bruises or anything. I don't know, but it was very thankful. Everything worked. Please make sure you know how to handle clocks. This is not an issue I can talk about other than that, but please make sure that you understand how clocks work in your program controller and that they're synchronized. Okay, so here are examples of actual programs that can be used to program various types of application. What is this? This is a seal circuit. Notice the seal in here. This is the seal circuit. Here's the pump run, and here is a pump run, and that is a, let's see, this is, how does this work? Stop. This is the start button. And this is the, this right here. And it, okay, delay time. This is a stop one. All right. Oak is allowed to start a timer. All right. So anyway, this is a seal circuit. This is a timer delay that seals. This seals with this. So again, this goes through and this seals that. Now, what happens when you're starting a pump with a low pressure switch so that you want to turn the pump off if you have low pressure? You have to let the pressure build up first, don't you? So you push a button and have a time delay. How do you build a dam? You let the water go around the dam for a while, and then after a while you seal that extra path up, right? It's exactly what you do here. You seal, you don't allow that. This is the time delay. And while that time delay is going, it'll run because of this. This has not timed out. When this times out, what do you have? You have a low pressure switch that sits there and says, if I have low pressure, after that time delay, I'll shut the pump down. And that's what that does. It's the way timers are used. And timers are used like this a lot to make sure that you get a starting circuit to 30 seconds to ramp up. And if it doesn't work, you shut it down. You give it 30 seconds to get high pressure. Here's another one. So here I have this is not real. This is on my kitchen table, and this is a play conveyor. This is not a real conveyor. But as this conveyor turns, this proximity excuse me, it's the metal going by, this flag going by, all right? Now, it's a simple circuit, but notice what happens. When you have a flag like that going by, you get a pulse, right? And if the pulse does not occur, you don't see an off to on or an on to off, what happened? Either the flag broke or the conveyor stopped. But in any condition, you want to know that the probability of the conveyor not working is pretty high. All right, if there's no pulses, the probability of something bad happening is pretty high. Either the proc switch broke, the flag broke, or the conveyor broke, or the motor stopped. One of those 4 or 5 things had to have happened. So you're looking for pulses. How do you do that? Well, you time a circuit so that you actually see a time delay either on or off. Either on or off, and if either one of them happens, you say an alarm, you set an alarm. In other words, if it's been on too long, alarm. If it's been off too long, alarm. Either way, you need to flag and say, stop my conveyor. Either way, too much time on or too much time off, stop. So that's another example of a timer. They're very useful. You say, is that the only one? No, there's a lot more, okay? There's a lot more of this kind of thing. Also the kind of thing where you have a buildup, and then what happens? Then when the buildup goes away, you don't want to immediately turn on. You want to let the buildup go down a little bit. It's like when the bubbles come down below the level, you don't want to immediately turn on the microwave, because what happens, the bubbles will go right back up. You want to let it go down a little bit, give it about 10 seconds, 15 seconds, and then turn the microwave back on, and then it comes back up. Other things that you can do with this is like a motor. Can a motor be turned on and off too much? Yes, you can turn it on and off, and too many times, and it will break down the motor. So you have to be careful that you do not turn a motor on and off too often. You have to delay and let it only turn on and off at certain times. Okay, enough on that. Combining timers and counters. Okay, so this is a circuit that basically is a what? You would call this a noisy circuit, okay? On, then on for good. What would that circuit look like? A proc switch, a proximity switch. Proximity switches are noisy prone. Proximity switch, it's a noisy input, okay? Now, here's the problem. I had a guy say, well, I work for GM and we always had a half a second delay before we would ever bring a signal in from a proc switch. He smiled at him. Good for you. You know, these kind of rules sometimes have validity, but also at times they're very wrong, okay? So let's think about it. If you want this signal to definitely be on before you do some kind of an action, yeah, you're going to have a time delay. But what's wrong with that? If this is part of a machine that makes parts, and the more parts you can make per unit of time, the better the more money you're going to make. What do you want to do? Do you want to act here or do you want to act here? My opinion. Do you follow me? You want to see what I'm saying? The first instant that you can make that move based on seeing that part is here. It's not here. You may not agree with me. You may say, well, this is a solid input. It is. That's an input too. And that's where first solid metal. Proc switch, first solid metal. You see the problem? You see the difference between thinking in terms of, well, always or never? If you say things like, I'll always do it this way and delay half a second before I make sure that input is into my program, what have you just done? You slowed down the operation of your process by that amount of time every time that thing hits. Half a second delays can mount up, and they do. So my point is this. There are times when this is very appropriate. There are times when you act on that. Now, I'll tell you a bad story about this, and that is I actually had this happen to me one time, and I had written a program on the bench or in my room or my office, and it worked, 100% worked. I turn on an input, I turn on an input, and it worked, the thing worked, and it worked great. Now, what it did was it sent out a bunch of commands, and this sent out a bunch of commands, and I'll do it again, and it sent out a bunch of commands right here. The problem with that was that this had not been received back yet when this one started out. And this one would hang up my process. Guess what? I had to go back and I had to undo. Basically, this one was the one I would act on, and I would have to not act again until after I had heard back from this event and came back. So my point, and that is, you can have a program that is very complicated, and it was, that works with a straight input, but when you have this kind of input, it may not work. And I had a mess. I had 18 of these. And anyway, that's beside the point. But this was in it's for Chrysler out here in Perrysburg. Anyway, it was a reading of a RFID tag. So again, I'm just saying that you have to be careful when these signals come in. All right, so here is a race. What is a race? When you have two things that are competing with each other, correct? Here's a counter and a timer that are actually a race. Now, you say, this is never used in the real world. It can be. It's not that you will use this very often, but you can. And I'm going to give you an example of that. Now, this just happens at that time of the year that, whatever, it's late December, okay? and you're up at 3 a.m. because you've got migraine headache from, everybody trying to do all kinds of stuff. And you hear this commercial on TV, and this is the commercial. Ready for it? Everybody ready? This is the commercial. What is that from before your time? What is it? The clapper. The clapper is a race. If you have two hits, two inputs in a certain amount of time, a certain volume, it'll turn on the light. If you do slow, it will turn on the light. If you only do it once, it won't turn on the light. It's a race. It's a race between a timer and a counter. You ever know it? Exactly what it is. All right, and that's what this is. This is a 3. This is a 2. This is the cap. This is the timer. This is the circuit for the clapper in a PLC. Any questions? Any comments? Glad that there was somebody that admitted that they've been up at 3 a.m. and seen those commercials. Anyway, but did you ever think about it that way? Had you ever thought that that's exactly what it was? That's exactly what it is. It's a race. And this again is additional thoughts on that one I talked to you about before, because now instead of the box immediately stopping after the photo eye stopped, you want to space it based on a time delay from here to here. So you give it a little bit of time delay before you turn it off. Okay. And the counter you use to count up so many boxes, and then you make this into another kind of a conveyor. You make this into a discharge conveyor instead of a charging conveyor. So it's you use a counter, and it can go count up, count down, and then there's your counter upper and your counter downer. Okay. And this is your spraying of the part multiple times, where you go back and forth and back and forth and back and forth and back and forth. If you want to go 5 times, you put a 5 in the count instead of 1. So you're now counting. Do you see how this stuff just keeps building? It builds and builds and builds. These are simple circuits, but they're not simple. Okay. So again, that's a counter. Now, after all this, 3 types of timers. The Modicon timer was very simple in that it was 3 types of timers. There was a 1-second timer, a 10-second timer, a 2-second timer. That's all the timers that they had. But how do you get an enable a reset timer versus an unreset timer? Okay, if you have a non-reset timer, you just basically put a curl between here. This was the go. This was the IN, and this was the enable. Okay. This would enable it to turn on. So basically, they had a very good idea. Copy them. That's a very nice timer. It's one timer. It does everything. So my point is this. You can have one. That's all the timers that they had. Modicon was very smart. They were just dumb as a marketing company. Okay. And that's chapter 7. A lot of examples, that type of thing. Chapter 8. Now this chapter, in chapter 7, they kind of go together. They're very similar in the fact that they empty into a box. But there's 2 types of boxes in math. There's the comparison box, and then there's the execution box. Okay, so you can have both. Okay, so there's a box that acts like a comparison. And then there's a box over here that does math functions. Now these will not get you, an infinite series or whatever, but you can do all the add, subtract, multiply, divide, cosine, sine, anything you want over here that you can in normal calculator functions. These are calculator function blocks. Okay. The difference between Allen Bradley and Siemens is very little in regard and over here. Now the Siemens makes their contact look like almost like a regular contact, where they put something like that in, that means greater than or less than or whatever. Allen Bradley makes it a box, but they put them over to the left, like a contact, just like a contact. Okay, so again, that is this is the Siemens. This is the Allen Bradley. Other than that, they're very similar. Now, the difference between Allen Bradley and Siemens on this block is this. Allen Bradley uses a block called a compute, CPT, compute. Siemens uses a calculate block. They do the same thing. And most of the time, that is your best friend, is that. So here are your comparison operators for Siemens, less than, greater than. Now they both have what Siemens called an in range. Allen Bradley calls it a lim or limit, and it basically is a high and a low. If you're inside this, they pass power. If you're outside, it doesn't pass power. And if you flip the high, if you put the low here and the high here, if it's in here, it doesn't pass power. If it's outside, it does pass power. So this is the not of this. They do the same thing. They both do the same thing. If you want to do a comparison with a high and a low limit, and you want to know, is it outside the limit, pass power if it's outside the limit, you put the low at the high and you put the high at the low. So when it's outside the range, it's going to pass power. And that's the only difference. They do the same thing. They do exactly the same thing. Siemens calls it in range, and Allen Bradley calls it lim or limit, but they do the same thing. There are your math instructions. Now Siemens, there's your calculate block. Siemens has all of the inputs coming in on the left-hand side, and then they use these variables to do the calculation. What if you need more than 3 variables? You hit the star. And most of the time, anytime you have a Siemens application, that you need to add more to, you keep hitting that star and it keeps adding. It keeps adding more down. And if you have 20 variables, just keep hitting the star and go 20 variables deep. Keep hitting the star. So it's not limited. It's not limited to 2 or 3 or 4. It's keep hitting the star. Okay. Modulo, you got all the negative, all of them. Okay. Min and max, there's your limit instruction. Now, they both have floating point and they have integer math, and you have to be careful, except for the fact that now Siemens has a variable called a variant, V-A-R-I-A-N-T. So you have to pick usually the type of variable you want. If it's a number that is a counter, you pick an integer or a dent, double integer. If it's a number that you need a calculator number from with a decimal point, you use a floating point or a real, typical. But again, you can mix and match to a certain point, but then at some point you have to make a commitment which way it's going to be, which way your answer is going to be. But with the variant type, I'm not really sure because I haven't studied the variant type, but that variant type allows you to flip back and forth between them. With all these different instructions, I had to throw this block in. It's not one of the math instructions, it's not one of the comparison instructions, but you have to have this block in order to be able to do anything, and it's the move instruction. The move gives you the ability to move things around, and you have to be able to do that. Move, M-O-V-E, they both have it. With Allen Bradley, to bring an analog value in, you do a scale and normalize. With Siemens, you do a scale and normalize. With Allen Bradley, you bring the variable in already scaled and in its proper format by configuring the card that the variable is brought in from. Allen Bradley handles a lot of things by configuring the card that you bring the variable in from. Siemens brings it in and you scale and normalize it right in the program. One of the little differences between the two. Okay, so here is someplace is an example of a right here. Okay, so I have a variable. It's an analog variable. It comes in and it sits there and it turns on, it turns off, turns on, turns off, turns on, turns off, based on a comparison, right? It based on a comparison statement. So you sit there and it does that all day long. Is that good or bad? Typically very bad. You want to have a deadband. In order to produce a deadband, what do you have to do? You have to do something, and you want to do something like this. How do you do that? A number of ways work, and all of them do the same basic thing. Here is one of them, latch, unlatch. Here is another. What is this? This is a seal circuit. Does everybody see this as a seal circuit? When you're above the high, you turn it off, and when you're below the low, you turn it on, and it stays on until you go above the high. This is a seal circuit. So again, you use a seal circuit to do what? To give you a deadband between the high and the low. So you're using a comparison statement and a seal circuit to give you a deadband so that you don't have this, so you have this as an output instead of the other one. You don't turn on and off nearly as often, but you still keep your process fairly stable. All right? Why do you not turn stuff on and off like this? Solenoids turning on and off like this will wear out very quickly. Anything that does this all the time will wear out. They wear out. So this is a much better approach than the other one. Okay, that's typical of that kind of circuit. Okay, use of memory with comparison statements right there is, there's your deadband, okay. Now, all of your programmable controllers have status tables. They have them hidden or however you want to call it. But when you're programming along and you want to know whether the result of an operation gives you a carry or a 0 or a negative value, you can get at it. It's just how, right? You have a status table availability. So this is the older Allen Bradley. This is the newer Allen Bradley down here. Okay, the status table, and you can get at that. That's the older one. That's the old one still. But you can get at them. And also faults. If you have a fault, you can get at it. You can find out what it is. This is the, it's called runtime controller configuration and status bits. And you can get at these. And you can find out if what you had is a fault. In this case, I say Siemens has similar results in some of the following pages that shows you what these are, and you can get access to them. So if you have a fault, you can get access and find out what they are. All right. So, compute block. How do you remember the difference between Allen Bradley and Siemens on this block? Compute till you puke is Allen Bradley. Okay, compute till you puke is Allen Bradley. And mixing of counters and math, useful, very useful. And here's the variables, how you program them in the Allen Bradley. You actually program it as an expression. So basically, we've turned you loose. You can do anything you want to with any instruction in either PLC as of now. All right. So if you say, you didn't tell me how to use a blah, blah, blah instruction, I probably won't tell you very many more instructions how to use it. Do a few more instructions in chapter 12, but any instruction that you find that you think you want to use, you're free to use. Chapter 8. So, how do you do this now? All right. So you want to move from the fill to the condensate to the drain, right? You can put a status number into a word, and if it's a 1, you're in the fill mode. If it's a 2, you're in the condensate mode. If it's a 3, you're in the drain mode. Does everybody understand what I just did? I separated the 3 phases of this operation into a numbered system, 1, 2, 3. It's a state table is basically what it is. We're going to learn more about states in chapter 11. But basically, I made them states, and I used numbers to do that. Any questions? Now here's a paper making process, okay? How do you make paper? Well, you throw in pulp into this big tank and you throw in some other stuff, things that glues and stuff like that, and then water, a lot of water, and you stir it a lot, and then you pump it out into kind of the inverse of a manifold. Everybody knows what a manifold is, where it collects the gas off of an engine and then puts it out to a tailpipe, right? Well, you do the opposite. You actually spread the pulp out onto a moving screen on a conveyor. So you got a conveyor you got a conveyor that's got a Holy conveyor. All right, it's got holes in it. So you have little bitty holes, and you suck the water out by having fans that are sucking the water out underneath the conveyor. So you spread it out, and then you move it along, and then you run it through a dryer. All right. So how do you make this? How do you make this? How do you put this pulp into this big vat? How do you do that? Well, you put a loss in weight feeder up here, and you put a vibrator system on it. You put your box here, and you say go. What happens when you say go? It captures the weight at that point in time, and then it shakes, and then it shakes, and it shakes, and then when it gets 500 pounds less than that, it stops shaking, and you've got 500 pounds of stuff in that vat. Okay, you say, is that how paper is done? I don't know how paper is done. I know that's how a fiberglass mat is done, because I programmed this. I programmed a fiberglass mat program to do exactly this. How do you do that? When you hit start, what do? You take a 1 shot and capture the starting weight. All right. Then you have a target weight. What's the target weight? Well, it's 500 pounds less than that. So you subtract off 500 pounds, or 500 to 300, whatever it's going to be, you subtract it off. Then when the weight gets lower than that target weight, you shut the system down. You put a seal circuit in to say shake, and when the weight gets less, you shut it down. Now you all can write a loss in weight feeder program. You have all the components to build a loss in weight feeder program. You didn't know that you could do that, did you? But you now have all the tools, seal circuit, 1 shot, compare statement. That's all it is. It's a very simple program. But you can take something that looks very complicated and you can write that program for that very quickly. And I think you see the value in some of this stuff. Some of this stuff is hard, but that program that I just described to you is what? A one shot, a seal circuit, and a compare statement. That's it. I think I wrote it right here pretty much like that. Anyway, it's a loss in weight feeder. Okay, so now we're stepping, okay? So what is a festooner? Right there's a festooner. It goes back and forth and 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 back and forth until you're done. Whatever that is, okay? It keeps going back and forth and back and forth. So what do? Well, you have an end here where it goes so far and it stops, and it goes over here, it goes over, keeps doing that back and forth. So what do? You count. You can use a counter that counts how many times you go back and forth. You can weigh it. You can look how much it weighs. You can stop based on weight. You see, is this done in the real world? Yes, it is. This is done in the real world. I worked on I did one of these at Owens Corning again, at the tub plant that they have in Huntsville, Alabama. They since sold that plant, but anyway, what they did was they made sheet molding compound, which is nothing more than the stuff they were making tubs. They were taking and making tubs for bathrooms out of this. So what they did was they would take the sheet molding compound and fiberglass, and they would put it like a sandwich. And they would have, on the bottom, they would have polyester, like a bag, like a, it's polyester, like a bag. And then they would have the sheet molding compound, and on top they would have another poly bag. So basically, it's like a sandwich going down the line. And at the end of the line, they would take it, not this thin, they would take it and wrap it back and forth. It's about that thick, okay? They would let it cure for a couple of days. Then they would take it and they would cut off so much of it. The guy would take so much, cut it off, and throw it into a press. And the press would come down. This is a huge press. It'd be as tall as this room, or bigger than this room, taller than this room. A big, massive hydraulic press would come down, heat in it, and the pressure would basically cook and make that tub its final shape, okay? And make the parts for a tub. It wouldn't make it all at once. There's 3 or 4 parts to it, but that's how it did it. And I think, did they paint that, or did they, I don't know if they painted it or not. They may have painted it. They may have come out ready to go. I'm not really sure. I don't remember anymore. I didn't do that part, but I did the festooner. And anyway, I'll tell you another story about the festooner. The first time I put this thing together, I had a little DC motor that went back and forth and back and forth, and you tell it to go forward, you tell it to go reverse, you tell it to go forward, go to reverse. And I did not pick a regenerative motor starter. I didn't pick a regenerative DC drive. I picked one that had a contactor that went forward and back. And after a few minutes, I smelled something. I was running it. What is that smell? The contactor's burned up. Okay, so if you have a motor that you run over, and when it's still going in the forward direction, you tell it to go in reverse direction, a DC motor, it turns into a generator, and it makes those contactors, it eats them up, it smoked them. So I said, I think I need a regenerative motor starter, and we ordered one, we got it in, and it worked fine. But again, lesson learned. A regenerative motor starter does wonders. But that was then. Anyway, I don't want to belabor that one, but that's another counting problem. It's another accounting problem. Okay, so we talk about number systems. We've already done this. This is not something new. We've already done this. And I want to get through this really quickly. Now, this is a program that does what? This is a program that you can actually do. I think this is the last 2-point problem you can do. Okay, I think that this is 8.1 is the last of the 2-point programs that you can do, and then the latter part of this chapter you can do a 4-point problem. This is a 2-point problem, but you can do it with Siemens and Allen Bradley, and it's pretty simple anyway. And here's if you want to make a two's complement, there's the two's complement. And down here is the first 4-point program you can write. Excitement. Drum rolls, please. Okay, this is where you can actually make a 4-point program and make it work. So basically, what do you have to do? You have to wire this guy, and it's easy. And what actually happens with these little servos is you create a number that is bigger or littler, and it makes this little arm go one way or the other. Okay? And it talks about how to do that. I think I give you part of a program for that as well. So you don't have to start from scratch. This is a Siemens only program, by the way. I show you how to do PWM pretty well here, okay? This is lab 8.2. Anybody needs some help with this, I'll be glad to help you. But anyway, there's several of these in the lab up in 2350. And you can take this thing and make it go open and close and open and close. It's the first 4-point lab, and it's a nice little lab. Okay. I talked fast, and I went through 2 chapters tonight. I hope you don't get too upset with me. I hope that you at least got something out of this. What can I ask you on a test out of chapter 7 and chapter 8? We'll talk about that on Wednesday night, and we'll go to chapter 9. But I want you to understand some of the problems that I can ask you. I'll review some of those. And also, there are old tests that you can look at to study for the test, and those are on the website as well. So you can do that as well. Anybody have any questions? I talked really, really fast. I know that. But I want to get through some of these chapters. I want to get to chapter 11 before the midterm. I honestly think chapter 11 is kind of the break point between really chapter 13, but chapter 11, I want to get through chapter 11 before the midpoint, because I want you to have that in your head before we get into the second half of the course. The second half of the course turns out to be pretty much what we call big box instructions, okay? Not all of them are, but a lot of them are just massively big instructions, and how do you make them work? And not all of it is that way, but there's a lot of it that's that way. So I want you to understand that the not simple programming, but the glue that makes everything work is in chapter 5, 6, 7, and 8. And after that, then we start getting into these big box problems, and that kind of they kind of engulf you. I don't want to make it such a bad thing. Okay, talk to you later. We'll see you. Have a good day.